بسم الله الرحمن الرحیم ولا حول ولا قوة الا بالله العلی العظیم حسبنا الله و نعم الوکیل نعم المولا و نعم النصیر. Today we will continue on the topic of motion control of the robot in joint space. In last session we discussed about how we can use a simple PD or PID controller, which is the most significant or the most used, frequently used controller in robotic manipulator, especially in industrial robotic manipulator. And also we showed that the weight of the robot, if it is not compensated by mechanical structure or any other means of weight compensation, will cause either a steady roller or a delay if we are using a PID controller. Here we practice a second method that is provided to you and taught to you in linear control system, which is a feed-forward control. A feed-forward control usually consists of two loops, or one loop which is from the measurement, as you see here, from the measurement we go back to the system as before, the structure we had before. But since we have some sort of disturbance in general, in our case the disturbance is due to the gravity, we add another controller, a second order, or a second controller, which we call a feed-forward controller, to compensate particularly for this disturbance. So usually the steady state error can vanish with that structure, if with some condition that we will see. For now, I performed the theory of linear control here. I review that. Of course, you are familiar with such structure. Why we call this a feedback and this one a feed forward? This is because we have to measure the Q just instantly on time to get the feedback, and this is the structure of a feedback. But for this loop, as you see, we don't need to measure QD. Of course we can measure, but we don't need to measure that, because this is come from a trajectory planner that we talked about before. We know what is the QD beforehand, and that's why we don't need a measurement here. We just use the structure, the information that we have already taken from the feed-forward controller for the trajectory planner in the feed-forward controller. And you see that this is forward and this is feedback. But the main importance difference is this is usually used by no measurement unit or by the structure of the system. And particularly we would like to examine the effect that this feed-forward controller can have. Here we have a 2 degree of freedom controller, we can say, or 2 independent controller. Before we had only a controller. Usually in control system we have only one controller, and so we have some limited practice. If it is a second order system, for example the final closed loop system, we can have only 2 parameters to fix. But if we need to have more than 2 objectives to come here, usually we use either another loop, which is here a feed forward, or sometimes another feedback, a cascade controller, which we will discuss it at the end of this course. Now, if you look at this, we can write the closed loop transfer function here we have one loop, the other loop. We can use Mason loop or Mason rule or any other means to simplify the controller, the structure, and see that you have the transfer function or the characteristic equation comes from the feedback loop. So we have 1 plus CIPI as before, the loop gain 1 plus L in the denominator, but in the numerator here we have a F times C, because this is also coming to the picture, F times P for the trajectory input, and P comes here. As you see, from this input we have only P here, P times the GI, or the input that is come from the disturbance. And this disturbance could be non-vanishing, could be a step function, could be something that we would like to take care of that. Now, this is the closed loop transfer function from the two input, the trajectory one, the disturbance ones, to the output system, the position that we are controlling of the robot. Now, if we just make some further manipulation and find the error dynamics, finding this EQ here, it is very simple to just find the EQ equal to QID just QID minus 1, and this will reduce to something here, 1 minus FIPI over 1 plus CIPI. So we have some zeros here, some poles here, and here we have just a simple PI over GI. Here it is negative and here it is positive, because we have used QDI minus Q here. And this is very interesting, because here we have something in the numerator which can be equalized or set to 0. Compare that to the previous case that we don't have any feed forward. This would be exactly the same, but this is different. We have some zeros here, and we can use the power of 0 here. If we could particularly design this F, we have a controller here, something that we can design. If we can particularly use the power of F to make this equivalent to 0. So if this is equivalent to 0, or the design variable F, the design controller F, is the inverse of PI. With some restriction, with some assumption, this could be possibly be done. So if Fi is equal to Pi minus 1, this is equal to 0. Even if we cannot do it exactly 0, we can find it, in a bandwidth, make it 0, or somehow make it very small. And this is not by using a large gain F, but a smart gain or a smart controller, which is actually the inverse of the plant. This is the essence of the feed forward. So that how the gravity or the disturbance is coming into the picture, learn the dynamic of the system, get calibrated, get to know it, and use this dynamic in inverse form as a controller. Just something is being added here, the inverse controller will subtract that, and that will make this part equivalent to 0. So the error, regardless of what you have, the error will be cancelled basically, and the error will go to asymptotically converges to 0 by this means. And of course, this part will also contribute to the controller and to the error, and then we can, by having a good design, the CI, this part, as you see, we have P over 1 plus Ci Pi, and then we can also reduce the effect of the disturbance in here. This is always very interesting to have a 1 minus something or A plus B something that is a design parameter to make that part equal to 0 to find the structure that we have. This is a general case when we have Pi, Gi, Ci, but in particular for a robotic manipulator, the P is quite known. We know that the P is a second order system if we have a calibrated model in this here, and then the feed forward should be somehow the inverse of that. And as you see here, the inverse of that is we call P2D, the second derivative as we have here. This also should be BEIS, S should be here. So this is exactly the denominator of here comes in as in the numerator of here. Of course, in real implementation, we should take care of that because this is non-proper. This is also non-proper, but we can implement that in a high bandwidth frequency by adding some filter, some poles at the bottom. Now, if you use this idea of inverse plant as a feed-forward controller to the robot, then you can see that your aerodynamics, due to this, the aerodynamics would be a linear part, very, very good design as before, regardless of what is GI and what is your different other part, plus GI. And the GI is the disturbance that is coming to the system. Still, we have not completely removed the GI, but by setting the KDI and KPI, I hope that you followed what I had given up to here. I told that this gives you a second order system, so you can design KDI and KPI as we talked in the last session. Very easily to have a second order with zeta equal to 0700, 707 with very particular case. But still this G has not been removed. So what we can do with the same idea of having a feed forward here, that this is the last point in a feed forward control, if we can calibrate that, if we can find what is the GI, if we know beforehand, for example, at each point or at each configuration, what is this GI as a function of time or as a function of the trajectory, then we can have another feed forward case. We know that this is 2, for example, Newton meter, or 2 newtons depending on the structure, and then we subtract that exactly as we have done it here, put it a -2 there, or if it is a function of time, if we know or we can calibrate that as a function of time, then we can compensate it exactly the same way that we are going to do that. Of course, feed forward is not that accurate because we are not using feedback. We are just using the knowledge, the a priori knowledge of the system, not the real-time knowledge that we can get from the feedback structure. By this means, we can conclude the linear controllers. Of course, then that we can have here, I just name some of them to you and summarize that. So what we have given in this part is a simple PD controller. Then we add an integrator to it to take care of the steady state error. And we saw that the PID, the integrator part, is somehow giving some lag to the system. Then we provide a feed-forward controller. As you see, the feed-forward controller is examined to take care to use the zeros of the system to make the error exactly equal to 0, not just for the step input. If we have basically this equal to 0 for any input, like a quadratic error, linear parabolic blend, something, a quintic, any type of trajectory, we can have a 0, and then to take care of the gravity term, we have a feed-forward term added to the system. But this is not the end of the linear controller. Of course, you need some more advanced linear controller to be designed as well. Maybe one of the most significant ones, since we have a model for the system, but the model is not accurate, a robust H-infinity linear controller, which we have also implemented that in many of our robots. That requires a bit more theory, and this is taught in our linear robust control course, and I have a book on that. I just recommend you, if you need to know how this works, this is also very practical and based on the experiment, but we don't use just the nominal model for the system. And in linear H-infinity control, we say, okay, this is the nominal one, and also somehow encapsulate the uncertainty. How much accurate is this model? And if you have these two information somehow bounded, and then you can have very effective and very celebrated method here that are used in the controller. So always you can have some robust defying or robust controller to be added to the system. Of course, there are some other model predictive controller, some other approaches, even fuzzy controller to be implemented in terms of a robotic manipulator. But as the final word, in industry, they use usually a PD or PID with a small gain of I plus gravity compensation. The gravity compensation is very important. It could be either done by the controller, by the feed-forward. It can be also done by some mechanical system added to this to the robot. Any questions now?
May I ask a question?
Sure.
Does adding a feed-forward affect the speed of the system?
Again, if you add a feed-forward, does affect what? I didn't get your question.
The speed of system.
The speed of system. Yes. Of course, the main important to add feed-forward is not just the speed. The speed is basically set by KPI, the omega n in the closed-loop system. The main importance of the feed-forward is that this part becomes 0 or very small, if you don't say it is ideal. And this means that for any input trajectory, for any trajectory that we have some 0 steady state error. And this is the main advantage of using feed-forward. But usually the main part, the cornerstone, still the PD controller. Here, the main controller that it is in the feedback. And usually the speed, the transient, the overshoot, everything can be set up by these two gains as we had before. But it is now much easier to set up these gains.
Other than the need for having the model, does it have any other drawbacks to use feed-forward?
Of course. The model should be invertible. So if you have a non-minimum phase system, you will add the inverse of that, it becomes unstable. I don't say it becomes the closed loop system becomes unstable, but you're adding something, as you see here. You have a very good and stable system. You are adding a unstable controller to it. And this is not usually very practical and very preferable.
Thanks.
Now, let's start with the multivariable controls. Yes, Hussein? Go ahead.
Concerning the mechanical compensation of the gravity.
I still don't have your voice very clear. About mechanical compensation of the weight?
Of the gravity.
Okay.
Okay. We must consider the gravity constant in order to compensate it mechanically?
No, it is usually not. This is a good research, a very good research. Let me just use, I hope that this is working. Let me just use some, since we have internet, we have gravity compensation robot. Let's see, for example. And then go to the images. You find many systems that can be used. Let me just see, for example, you can have some spring here to have some, or this one, for example. These are practical. This is also somehow surgical robot. But this one, I like this one much more. Let me, if we can have this open. This is also surgical. I just searched through. Anyways, let me open that. We can. There are many means. Oh my God! This is the program. Many means to see the graph. A static balancing method for variable payload by combination of counterweight and spring. We have usually three methods: counterweight, spring, and we can have also some variable force or variable which comes from a pneumatic actuator or a hydropneumatic actuator if the robot is very large. Of course, you can read that through, but usually if you have a parallelogram, what you have in your project, so the weight is not compensated as anyways. But you can, add some lengths here, as you see, and add some, compensating weights here. If you have a weight in here, like you're just using another weight in here, that reduce to make the center of mass coming exactly at the pivot point. So this is good in terms of reducing the weight of that, but you know that this will reduce the weight, the mass, but will increase the moment of inertia. So maybe the mass matrix is not equal to 0, but this would be like that. Either we can use also some springs. The springs, also if you look at the table lamps that you have usually on your table, there are some springs there, and you just move it, it will stay anyway in the space. Or a combination of them that could be used for gravity compensation. In this paper, it is looking at different rays or the effect that this can cause into the system. And this is a real one. You see that you have a counterweight in here. And you can have also some wires and some springs coming into the system to counterweight for that. But in our main robot and in many other robots, let's also consider, for example, KUKA robot, old version of, let me show some pictures in here. Here, you see here. Again, if I open that, I hope that that doesn't take too long. Sorry, I'll look at here, for example. You see that what we are using in many robots, not in all the robot, but the robot becomes larger in the workspace. Yes, we have some chipping sound of bird, just especially for you. After the exam, you need some remediation. As you see here, we have two links here, one here and here. Again, here we have a parallelogram. You have that in your assignment as well. And since you have a parallelogram, you can use a counterweight in here, or use a electromechanical or some pneumatic or hydraulic cylinder here to compensate for the weight. And here you have, again, you can see that you have two links coming to the picture as in here. And in many older version of the robot, not very new one, the new one coming, without counterweighting, as you see in here. The new ones, the power of the motors. But if you go to the older version of that, you will see such indication much in the system. As you see here, you should add some weight if you don't have a parallelogram here. But you see here, for example, this is an old version. This is and you see again a parallelogram, and this parallelogram will help you to have some counterweight here and the motors coming into the picture. All right. Look at here. You see that you have a counterweight in here. Again, it takes a while to come, but anyways, no problem. You can just make it, open it a bit. Again, this is another paper, MPI, that shows you if you use some sort of spring or counterweight, as you see, if we have a parallelogram, then we can add a counterweight to it. I would like to give research on that topic, but since you have so many other things to do, I will leave it for the people who, for the interested, actually for the interested people to see that. And you see here, for example, this is also good. The picture is not very good, but as you see here, you can have a cylinder coming here and have some sort of pneumatic counterbalance system. Okay. Now go back to variable control. The multivariable control, which is also very practical and we use it in a lot, is when the linear model for the system is not quite accurate, and we go to the that we have a consistency measure, a higher consistency measure than 30%. This means that, or we call it, when we don't have the gearbox, very high gear ratio there. We have a robot with gearbox of 30, for example, 25 gear ratio. In these cases, you cannot completely neglect the nonlinear model for the system. You have the ME and the CE and BE, but the M is, you have the mass matrix of the system, the multivariable and nonlinear mass matrix, but you have added here some moment of inertia that will balance these two together. If eta is very, very large, more than 100, then exactly neglect this part and just use this part and go to the linear part, linear controller that we have. But this is not always the case. Especially in some cases, we have some controller or some robot without any gearbox. If we would like to have very high speed manipulators, we reduce the gear ratio to a small number, or just we neglect that and we use some direct drive motors in the cases. In that cases, if the eta part is not dominant, then you have a nonlinear system and multivariable system. With M, I call it ME, is the effect of the viscous friction that comes from the motor side, as we talked in here. These are exactly, if you go to the last chapter, the dynamic equation that we got from here. Just before going further, I just mentioned a note here that what would be M dot if we have ME like that? What would be the M dot? You remember that we have the properties of skew symmetricity property. M dot minus 2C is a skew symmetric matrix for it. Now, I told you that now we consider that the system has with the full dynamic, we have this part here. I was talking about M dot minus 2C. As you see, ME is two part, and if you take the derivative, since these are all constant, the derivative of that, time derivative of that is becoming to 0. So ME dot is equal to M dot. So we don't really change the properties of the dynamic of the system. We are having some sort of this. And if eta is very small, let's say that, you don't have, you can just neglect this and go through the same old previous dynamic model that we have. MQ double dot plus CQQ dot plus G is equal to tau. Now, here, everything is vector. So this is completely multivariable. We have, for example, 6 degrees of freedom. Q is a 6 by 1 vector, and we have a multivariable system. Furthermore, it is nonlinear, because as you see this part, the gravity part that we saw, it is really difficult, and we should take care of that. Is nonlinear. It is depending on the sine of Q, cosine of Q, depending on the structure of the motor. And more than that, the CQQ dot, the Christoffel matrix, was the most difficult part of the dynamic equation that we should get. Unfortunately, you didn't start working on the dynamic assignment. Of course, you know that the dynamic assignment for your case is for the robot that we started from the beginning, so please use working on that, since we don't have that much time left in the course. But here, as you see, we have some sort of nonlinear and multivariable case. Since it is nonlinear multivariable model, I don't say we have to, but it is very natural to use a multivariable and nonlinear control for the system. And the multivariable and nonlinear control is something add up to the previous controller that we have. We have a PD controller or a PID controller before. We don't throw it away. We use that. We add something up to it. So the controller that we are discussing here is somehow a bit more advanced and a bit more involved. Note that since we have nonlinear control, then you cannot use this simple Laplace transform. You know that the Laplace transform, Fourier transform, is defined for linear time invariant systems, and these are useless. So the S dot, these are just gone, and we should talk everything in the time domain differential equations. Furthermore, some theorems that we have, like final value theorem, initial value theorem, the Laplace theorem, the let's say convolution integral that is coming to the multiplication, all the benefit that we have in the linear part, it is gone. And the only theory that we don't have any Routh-Horowitz, we don't have any characteristic equation for the system, since we don't have Laplace for a nonlinear system. And the only method that we can use is Lyapunov. Not the only, but the main or the cornerstone of the method is Lyapunov. Last time I asked everybody that how much you are familiar with Lyapunov stability. Many of you have taken a course, at least an introductory course about the Lyapunov. And for the one who have not taken, I recommend you to read the appendix of my robotic book on parallel robot. It has a very concise and practical case. Of course, the videos, movies, and the slide of my nonlinear course is also available on the net on my homepage, as you know. And you can also go through that if you would like to have a further read. But we don't need that much detail. We only need two theorems. The first theorem is the Lyapunov direct method that you should know, and the second one is LaSalle-Krasovsky method that is used in here. Anyways, without going through the detail of theoretical aspect, just let me know if you need to have a review. Maybe we can add another course, another session to review the nonlinear course. But for now, we just go ahead and then we start with the simplest maybe possible controller that we can use for the system. And the simplest possible is it comes from the last part that we have. Now we have a robot. Everything is vector now. We don't have, at the previous case, you see everything is unvector. It is decentralized. For each joint, we have a controller. But here, we have a controller for the multivariable case. So Q is bold. We consider that there are some disturbance torques comes here. Not the gravity. The gravity is inside the robot. It is inside the robot dynamics. So we have the gravity embedded in here. But other than the gravity, maybe we have some other disturbances. We call it tau d. Everything is in joint space. And the structure of the controller is is borrowed from the previous one. We use a PD controller, but a multivariable PD. Here, as you see, KD and KP, they don't have any index I. There are two matrices, and we use some diagonal matrices. If it is 6 degree of freedom, KP as a 6 by 6 matrix that at the diagonal term we have some PD gains. They could be different for each case, which is usually the case. It could be also all with the same gains. And KD is also the same thing. We have a n by n matrix. We use it usually diagonal. It could be also not diagonal, but for the sake of simplicity, we use a diagonal cases here. So we have the feedback. We have coming here, but the feedback, we don't have a one measurement. We have, if it is 6 degree of freedom, we have 6 measurements. We use all the measurement of Q's, and we have to design the trajectory for all Q's. So we have a trajectory planner for all Q elements, and we find the error, but again, the error is vector. It is multivariable, and we fit it to here. The output of this, we call it the tau PD, which is basically the PD part of the control. This is not the whole, we have another term here. And the another term is also borrowed from the feed-forward case. You see here, you have, in the last part, you have the dynamics of here, the linear dynamic coming into the picture. We use here the nonlinear dynamics coming to here. But notice that we consider that we know the nominal value of ME, the effective M. So we don't know exactly what is the M, but we can calibrate it and find some close to real one here. We have BEC, they control the dynamic parameter, all hatted. The hat means the nominal value or the estimated value of the matrices, not all the matrices. And then also we use we don't use a feedback here because it's a feed forward. We use the same QD, the desired trajectory that we have before defined using quintic or cubic or parabolic blend. So the version that we talked here, we have a trajectory planner here, and the trajectory planner gives not only the Q but also all the derivative of it. So we know that we have Q dot. So we use the dynamics but feed forward dynamic, meaning that we don't use the true Q here, we use the Q desired. And we assume that the robot is working fine, so Q and Q desired are very close to each other. And we also assume that we know the value matrices of the dynamic system. We call it M hat, B hat, C hat, and G hat, and we give it to the system. So if you see here, there are two equations. Tau FF, the feed-forward torque that we are using, is the same old dynamic equation that we have here as before. I'll put the PE here, the Tau FF, I use it here, put it here. Is exactly the same old dynamic equation, but using the estimated value for the system. Now, if we go through the to see what will happen, is it good enough? But we need to analyze the closed loops dynamic of the system. Now, we don't have any characteristic equation, we don't have Laplace transform, but we have the differential equation in a multivariable case, and then we use that. So we have this system, and the tau is defined by these two. Tau is tau PD plus tau FF. We put it into the dynamic equation of the system and see what would be the closed loop dynamics. So we know that the tau FF is offline or it is feed forward. It can be designed beforehand, but the PD controller, it is still the most significant part of the controller, which is feedback based. Now you see that your dynamic equation MQ double dot plus B plus CQ dot plus GQ is equal to tau. The tau is all the taus that are adding to the system. I also added the disturbance tau here just to make it everything all together. So we have the tau PD, we have T tau F. These are the control part or the controlled torque to the system. And this is the disturbance torque, which is somehow annoying and we would like to reject it. Now if you look at that, now we can just write everything here. Tau PD was these two terms. Tau FF is these three terms. And tau desired is in here. So now we have a long dynamic equation. Multivariable and dynamic. To simplify, assume that you have full knowledge of the system. Assume that you exactly know what is the mass matrix. This is very important. To have the dynamic equation, first, find it right. You should find the mass matrix right for the system. If you have some miscalculation there, you come into the trouble here. Not only the dynamic equation itself, all the parameters like masses, like moment of inertia, and so forth and so on. So this is usually done by some calibration process. But assume that we know everything exact. This is a not very practical assumption, but it is an assumption. Furthermore, assume that the robot is working well, so the Q is very close to Q desired. So we don't have that much difference, steady state error, something like that. These are two together. To simplify this, if we don't do that assumption, we cannot simplify this very large. Of course, we can simulate it and see some simulation results, but no analytical approach can be found in here. Now we can do that, as you see in here, if ME is equal to M hat is equal to M, and QD is equal to this, these two terms will cancel out, and the same. This one will cancel this one will cancel this one, and tau d will remain. The remaining part would be ME. Here we have Q double dot D minus Q dot. This is not cancelled. This will remain because these two are still. It is very. Of course, you can assume that the second order of your derivative is also zero, but this is not really true, so we can keep that. Kp and Kd, your derivative comes in here, and your disturbance. And it is very interesting. We come to a picture, we come to an equation. It is not linear, but it is very, very close to linear. If this ME was gone, if you assume that this was not available, then it would be completely linear. It is multivariable. Still, we have matrix form, but all the C terms, G terms, everything is assumed to be cancelled out. And this is because of the feed-forward controller. This is the idea of the feed-forward controller. And this is a second-order system. And you know that a multivariable second-order system, you can, for each joint, now for each element, if these are diagonal, and we have an M here, you can consider that everything, so this is the error dot, we can write it in here. This equation is a multivariable second-order system. It has some positive point, we have feed forward, and some negative point. So you can design KPKD as you designed it in the linear control part, to have a good transition, to have steady state error if possible, maybe not, depending on and you can apply it to the system to see how this score works. M, KD, and KP will give you the natural frequency. The natural frequency at each joint will be the Kp over Kd, square root of Kp over Kd over M, and also the zeta comes from this Kd term as we talked in linear part. So if you spend good time on tuning the PD gain, then you can get a good result. And usually this is the first controller, first nonlinear controller that you have. You can access to that. It is very similar to the previous PD controller that we had. Even you can use the PD controller, the linear controller that you have before as a basis, and then just make it into a vector form, a diagonal form, and then implement it into a multivariable structure, as you said. So by suitable selection of PD gain, the transient response and the steady state error are shaped as required. We can have zeta and omega in here. The disturbance is always annoying. If this disturbance that comes to the picture is vanishing, it will be reduced to zero, but when time is evolved, then you have zero steady state error. If this is not vanishing, then it is not, the steady state error is not zero. And except for the mass matrix, the aerodynamics is configuration independent. This is also very important. Why it is important? It is in the process of tuning the PD gain. If you are using a PD gain, if you move the robot in here and tune the gain to have a very good variable performance, this is not good when we are working here. And yet you see in our arm is also the same. Here it's very hard. If you would like to work this way, it is much harder rather than doing this. Because as I mentioned, if it was configuration dependent, you design a controller here, it works everywhere. But still, since the mass matrix is configuration dependent, you cannot have in all position the same omega n and zeta everywhere. But it is almost close to a control. It is much better than a simple PD. This is much better than a simple PD because you are, canceling many of nonlinear terms if this assumption holds. The negative point or the negative aspect of this equation is the assumption that we are doing. We use that full information is known. We have a full information requirement. What does it mean, a full information? We need to know the exact M, the exact C, the exact G, B, and also assuming that Q is equal to Q desired. And this is out of scope actually, because usually we know that the controller, these two are not exactly the same. This will converge to zero. The error will converge to zero, especially for the transient response here. So usually the aerodynamic is not fully configuration dependent, and this makes the tuning the controller much harder. And this will result to our next controller, which is the most important or the most foundation controller that we use in the robotic manipulators. If there is any question, we can just go ahead. Okay, we go with this is multivariable control. We call it computed torque control in serial manipulator. We call it inverse dynamic control in many other books and references, inverse dynamic. And also in contour compute, in control community, if it is not robotic, it was a control course, we call it a full feedback linearization control. These are all different words for the same idea. The same idea, if I talk with the computer torque, it comes from the inverse dynamic. We know that in inverse dynamic, if we have the motion of the system, the torque that is required to find that motion was found by the inverse dynamic. Tau is equal mq double dot plus cq dot plus g. So if we know that m, c, and g, we know what is the torque that is causing here. Now we are feedbacking that, not feed-forwarding that. We use a feedback. This is the most important part here. A feedback that uses that dynamics in here. Of course, this has some evolution. I'm just giving the final one, which is the most important one, version of the computed torque. But usually we are computing a torque. We call it tau feedback linearization, or the computed torque here. I use different names. They're all equal to each other. Some papers are just dedicated to computed torque control or inverse dynamic control, some of them call computed torque control. Doesn't really matter. So just to go through the to remedy the drawbacks, we still assume that we know the knowledge of the system. We know M, Q, and C, but we don't use feed forward. This assumption was really somehow ridiculous. We cannot assume that Q is equal to Q dot. If this is the case, we don't need any controller. So we use the exact Q and Q dot in here. I added another term here, and we never, ever feedback Q double dot, because this is practically disturbing and very, very hard. Usually we measure Q. We can have one differentiation by filtered differentiation, as we discussed it previously in the calibration process. We can have Q and Q dot, but never ever use Q double dot. If you are using Q double dot, you are in trouble, practically in trouble. Of course, in theory there is no problem, but in practice there is a lot of difference between theory and practice. So we feedback Q and Q dot. As you see, G was a function of Q, C was a function of Q and Q dot, B is also BE is a function of the viscous damping of the motors, but you need the Q and Q dot to find that. So tau feedback linearization part is B C Q dot plus G hat Q. This is not the whole case. We need a PD controller as well here, as before. And this is also very, very significant and important. Don't forget about that. Don't think that this is more important. No, still the linear controller is important. So we have the linear part in here, and we add another term we call AQ. This is like acceleration term that is, or a torque term that is somehow defined by, as you see here, Q double dot D plus KPD KD, KPE KDE dot. So we have this error coming to the PD controller. This gives you the PD part of the controller. You add this to Q double dot. This will give you AQ, and then you multiply it by M. So you have M hat plus tau FL. And this block diagram is exactly what you are doing, and you should implement that in your microcontroller or the controller that you are using for the robot. And this is very, 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 very powerful and very good. Now, without any further discussion, we go to the closed loop systems. To see what is the closed loop system, we don't have that much time left for this course. We can go to the closed loop dynamic. This was our dynamic of the system. M Q double dot plus B plus C Q dot plus G was equal to tau plus tau D. We have a disturbance here as well. But this tau, as you see, has two terms, the feedback linearization one and the PD controller one, MAQ plus TF, and then you can replace AQ by Q double dot, this plus this, and the tau FL we can put by the nominated value of that. So the controller, as you see, has 1, 2, 3, 4, 5, 6 terms, different terms, and all of these are multivariable and nonlinear. Again, it is very difficult in general to talk it. Let's simplify and see what will happen if now we we have good knowledge of the model of the system. If we know the model of the system, it means that the m hat, b hat, and c and g are equal to their real values. If this is the case, so it is very important that, you know, the terms will goes on. These are will deleted completely because we are using the feedback. This term is equal to this one, this equal to this one. Here we have me q double dot d, here m hat, and here we have m. And m is equal to m hat, but q is not equal to q double dot. So this comes also together, comes out of the picture. Since the m is multiplied by these two terms, this comes out of the picture. And this is the most significant part, that we put the m in here. We didn't put it m here. This might be coming to the picture at the beginning, but this is not the right case because of two reasons. If we put m in here, then we need also q double dot measurement. This is, you know, prohibited in robotic. And furthermore, since it is in the feed forward, we are multiplying kp kd times this to this m. This will result in factorizing m of q out of the error dynamic. And we know that mq is a positive definite term. It is always positive. It is invertible. So this means that this can never become zero, and this error dynamics is equal to zero. If you have no disturbance, if you don't have any disturbance, we have a second order dynamic equation, which is completely configuration independent. It doesn't matter if we are working here or here. It doesn't really matter if it is here or here. And this makes the task of gain tuning much easier. You will practice that in your example and in your mistakes, especially in your project. It is really difficult to have a very good tuning a PD controller that works in all the configuration space, but here this is the case that we have, and we can much simpler design the control. Of course, you need still to do some trial and error to have some practice here, but you have a second order dynamic. You can have, for all the joints, you can have a second order system with very good natural frequency and damping ratio that you know. And of course, we have some actuator limitation. We cannot increase widely Kp and Kd. We keep it in the mind that we have some actuator saturation, and the control effort should be remain in the same case. So if I just conclude my this session by this case, the computed torque control or the inverse dynamic control, I just using both, or the feedback linearization control, is very suitable because we can find by suitable selection of PD gains, which is not very hard to tune. We can have a very good transient response and also good steady state error. Maybe the steady state error is not equal to zero if G is not equal to G hat. But if it is equal to zero, we have a second order system, and in a second order system you have zero steady state response to input, to step input. Of course, for the higher order might be not exactly the same. If the disturbance is vanishing, the steady state error comes to zero. This means that we don't have really zero steady state error in practice, because G is not always equal to GD, and also the disturbances that come into the picture might be not vanishing, might have some DC values. So this comes in the naturally comes to the steady state error. But you can reduce that by increasing the gain of the system, and the gain of the system can be increased up to the limit of actuator saturation that we have. The aerodynamics is configuration independent. This is the most important aspect of this compared to the previous one. And the PD gain selection is quite easy. And this method is the base control method. I don't say it is the best. It is the base of many, many other control. This is the part that we are doing. The main idea is, the main idea can be seen at the end. A nonlinear multivariable system is reduced in the closed form to a linear, still multivariable, but linear configuration dependent second order system that we require very well. So these are the positive case, and this is very popular. Almost all the other method is founded on this basis. But still, we have some problems. Of course, the full information required is never whole practical. This is not true that we have M equal to M hat, G equal to G hat everywhere. Of course, we can assume that, but this assumption is not always true. So in this case, as you see, suppose that these are not equal to each other. This will give us some opportunity to work a bit more on some non-model based or robust approaches that comes into the next two sessions that we have. So as you see in here, M is not equal to M hat. Then here we saw very simple that this is equal to 0. But then this is not equal to 0 if these terms are not vanishing. You see that the difference between these two, B, C, G, and also tau D, multiplied by M hat, since we have M hat here, these all goes into the other side. All of these comes into the picture. This is a long nonlinear term, but this is not necessarily very large valued. Is it correct that M is not equal to M hat? But 90% it is correct. So we have an M which is reduced by 90%. If we are, I'm just saying 90%, it's just the approximate value. So we are reducing the nonlinear terms. If you are not canceling them, if you are not linearizing that, theoretically, we are using feedback to linearize the system. This is true if we know the parameter of the system. If we are not accurate at that, we are not fully linearizing them, but we are reducing these terms by 90%, depending on how well we know. If we know that well 99%, only 1% of the nonlinear term will remain. And this means that to use such thing, we need to do very accurate modeling and also very good identification. If we don't have the identification or the calibration in robotic, so this is not good. How well we are doing, still something will remain. So this remaining part can be considered as an external disturbance. And you know that a controller, a PD controller, is very well acquainted to reject this disturbance. So this, with the power of the feedback and with the power of linear control, we can go and combat this nonlinear part terms. And we can see that these external disturbances can be attenuated by high gain PD gain. And the only limit is we cannot wildly increase the gains because of the actuator saturation and also the noises that we have in the system. We have a trade-off here to find what would be the system. And the final thing, this is a model-based control. Why? Because we are using M hat, G hat, And for any model-based control, the controller is not robust. It depends on the model. You see that. But we can see that we can robustify that. This is more advanced and we'll go into hopefully in the next session or the session after that. For being with me, I guess this is all I would like to say for today. If there is any questions, any comments, please.
یه سوالی دارم پیش اومد گفتم الان بپرسم. این تو موقعی که تو IDC پروسه خطی سازی فیدبک انجام میشه، من الان یه ترم‌هایی میبینم، ترم‌های BAE Q dot که اگر درست حد زده باشن ترم‌های استحکاکه، درسته؟ بعد یه سوالی حقیقت پیش اومد، اصلا این سوال بیشتر به فصل قبل مرتبطه تا این فصل. فرض کنید یه بنده خدایی استحکاک رو BAE Q dot تخمین نزده باشه، BAE Q dot بله یه چیزی ساین Q dot تخمین زده باشه، یعنی در واقع استحکاکی که تخمین زده مجموعه ترم‌های ویسکوز و کولوم که خیلی واضحه که این تخمینی دقیق تری از BAE Q dot. بعد اون ساین Q dot رو بذاره تو لوپ تو پروسه خطی سازی فیدبک اتفاقی نمیفته. اشاره کنم که اون ضریبی که پشتش هست خیلی عدد کوچیکیه.
اتفاق رو چی ترجمه کنیم؟ Let me answer the question in English because Hossein is also. The question was, Alice said that we see here some viscous friction in the feedback linearization part. If we have also some Coulomb friction, can we do the same thing? The idea is the same. Of course, you can use it. But you know that in a linear control, if you have some discontinuous controller, you become some problems. You might have some chattering problem there. And especially if you overcompensate. If, for example, your Coulomb friction is 1 Newton, and you take 2 Newton out of that, if you overcompensate, then you make a very good, nice, stable to instability, and this is not good. So these two are the point that you should think about that. So you can compensate for that, but don't use the full knowledge. You make the minimum values that you have calibrated everywhere to make sure that the remaining part is stable. Okay, Ali?
من فقط برام همیشه سواله که چرا با وجود این که اون ترم کلوم هیچ وقت لوپ کنترل استفاده نمیشه و چی شناساییش میکنن؟ برام همیشه سواله.
استفاده میشه، چرا نمیشه؟ پیپرهای من ببین چند تا پیپر من دارم. نه اشکالش اینه سخت شناساییش. اگر اطمینان داشته باشه از شناساییش میتونه کاملا چیز یه دو تا پیپر من رو هاروارد نگاه کن. اصلا
دیدم من حتی اگه تضمین کنیم که اون کانسیستنته میشه استفاده کرد تو لوپ.
بله.
بعد مشکل چترینگ به خاطر ساین ایجاد نمیشه
اگر اوور کامپنسیت بکنیم. اینجا خودش معلوم میشه. وقتی چترینگ شد میفهمید زیادی استفاده کردی، کمش میکنید دامنش.
من تشکر توضیح.
مهدی آرمون.
سلام.
مهدی جان بود. سلام عزیزم.
استاد وقتی می‌خواستم بپرسم مثلا دلیل داشتش که فیدبک سرعت به این سیستم کنترل موقعیت اون اضافه نکردین؟ که دربارش صحبت نکردین؟
فیدبک سرعت که داریم، چرا نداریم؟ منظورتون چیه؟ چرا سرعت رو به عنوان دیزایر ولیو نمیگیری؟
بله مثلا برای کنترلش مثلا کنترل فقط موقعیت رو داریم تو اینجا بررسی می‌کنیم.
یه ربات به من بگو که میخوای سرعتش رو کنترل کنی. مگه ربات یه دره که میخوای سرعتش رو کنترل کنی؟ ربات میخواد یه چیزی رو حرکت بده، جابجا کنه. سرعت توش هست ولی واقعیتش موقعیتش مهمه. کجاست این؟ مثلا تو میخوای فرض کن که الان این آبو برداری بخوری، این آبو برمیداری حرکت میدی میاری، سرعت داره میبینی؟ ولی مهم اینه که این بیاد یه جای مناسبی، اینجا نریزه رو سر من، رو گوش من، اینا. این یعنی کنترل موقعی. موقعیت مهمتر از سرعته، یعنی پایه‌ای تره. اما اگه نگاه کنی تو همین لوپ هم اگه نگاه کنی ما سرعت رو هم فیدبک میگیریم. وقتی کیو رو بر حسب زمان داریم یعنی کیو دات رو هم داریم. وقتی ما اینجا کیو رو دیزایردش رو اینجا وارد کردیم یا توی این فید فوروارد، ببین اینجا وقتی کیو رو وارد کردیم کیو دات ها رو هم داریم. این نیست که اینا رو نداشته باشیم اصلا دقت نکنیم. اما اون انتگرال دوم اون اصلیه پوزیشن و شما میبینید که ما میگیم موشن کنترل. موشن یعنی
متشکرم.
Any other question? So it seems that we don't have any question by Fatima, Zahra and Hussein, and this is particularly strange, but we welcome that. خیلی متشکرم از چهچه بلبل، حتما لذت بردید. ما اینجا تو محلمون موتورسیکلت خیلی حرکت نمیکنه بلکه بلبلا حرکت میکنه. انشالله امیدوارم که توی محیطی زندگی کنیم که با طبیعت آمیخته باشیم نه با مدرنیته کاذب. موفق باشید بچه‌ها. خدا نگهدار.